Okay, so we'll give you a definition of continuous function. That's it. Suppose, okay, suppose a function f is defined. The point must be in the domain of the function. Is defined at a number, okay, at the number a. That's about. Now then, f is continuous, said to be continuous. Okay, it's going to be continuous at a or at x equal to the a if, that's it, limit of f of x when x goes to a is equal to the f of a. You see, that's it. So you find the limit of the function. Remember in those problems that you did, sometimes you find the limit and the value of the function. Sometimes they were equal to each other, and sometimes one of them didn't exist. But if you have both of them together, that's the estimate and the value of the function. If this is going to be true, we say that the f is going to be continuous at x equal to the a. If we can do this one for all the values in the domain of the function, we say the function is continuous on its domain, okay? So f is going to be continuous. F is going to be continuous on its domain of the definition, domain D, if it's continuous at any point in the domain. If you can repeat, if you can check this limit for all the points. If f is continuous, f is going to be continuous at all values. Okay, at all values of x inside the domain D. Okay, we say that your job is this one. Your job is to find out where a function is going to be continuous. Okay, from geometry point of view, when this would happen, this means the graph of your function is going to be one piece. There is not going to be any gap, any break in your function. So from geometry point of view, okay, geometrically, this is it. If this function, if a function f is going to be continuous, on its domain, then the graph of the function, then the graph of y equal to the f of x is going to be one piece, has no, okay, has no gaps or holes, if you like. That is going to be the case. So this is going to be, see, this is going to be the graph of a continuous function, okay? So this is the graph of a continuous function. But you see, but this one, look at this one, but so suppose you have this graph, you see, you have this graph, you stop and then you just pick the second part of the graph. If this is going to be the one, and this is going to be, the second part of the graph. You see, in order to graph it, I have to leave my pen twice, if you like. But for this one, I can do it. So there is a gap between this. This is a two pieces. So this is going to be the graph. Okay, the graph of this continuous function. This continuous okay, this continuous function. Okay, any question? So this is a situation that we're going to have. Now your job is, we give you a function, you are going to check for us. You're going to check to see if this function is going to be continuous, okay? So let's check. Example. The first one. The first one is going to be, suppose f of x is equal to x cubed minus 2x plus 1. What type of function is this one? Any suggestion? What type of function is this one?
Polynomial.
Excellent, polynomial. What's the domain of this function?
All real numbers.
Excellent, all real numbers. Look at how this one. Remember when we want to find the limit of the polynomial, we just substitute. So if this is going to be the case, for example, then, for example, if you want to find the limit of f of x when x goes to 2, since it's a polynomial, we already talked about it, we can substitute. So we get what? We get 2 cubed minus 2 times 2 plus 1. 2 cubed would be 8 minus 4 plus 1, which is going to be what? It's going to be 9 minus 4, which is equal to 5. So the limit is 5. But what's going to be f of 2? You see, f of 2 is the same thing. We know that because we substitute. F of 2, we just substitute, get away 2 cubed, okay, minus 2 times 2 plus 1, which is going to be 5 again, you see? So the limit of the function for this polynomial, the limit of the function, limit of f of x goes to 2, is equal to what? Is equal to the f of 2. So the value of the function and the limit of the function, they happen to be the same. So this means f is continuous. F is going to be continuous, for example, okay, at x equal to 2. You see, in a minute, we are going to give you a theorem. That theorem will tell you that if you have a polynomial, it's continuous always. You don't have to check this. We give as a theorem, okay? Any question? Let's have another one. See what would happen if the function is going to be discontinuous, okay? So look at this one. Number 2. This is, you will see these tabs quite a lot in your book. So suppose this function is given to you. Look at this one. Suppose your function is f of x equal to, this is the function. It is x squared minus 4 over x minus 2 if x is not equal to 2. Okay, if x is not equal to 2. And it is equal to 5 if x is equal to 2. Okay, so it's partition around the 2. So they ask you this question. The question is f continuous? Is f continuous at x equal to 2? Okay, you want to check the continuity of this function at x equal to 2. So what do you have to check? You have to check the limit of the function. You have to find the limit of f of x when x goes to 2. Then you have to find f of 2. F of 2 means the value of the function at 2. What is the value of the function at 2? Anybody? What is f of 2?
5.
Excellent, 5. F of 2 is 5. So we already got f of 2, so we have to find the limits, okay? So the solution is going to be, so we know that, note that f of 2, note that f of 2 when x is equal to, you see, when x is equal to 2, the result is 5. So that's the value of the function, the exact value. Now we have to check the limit. So the question is, what is going to be the limit of f of x when x goes to 2? You see the limit. Now let's find out what's going to be the limit of this function. So in order to find the limit of f of x when x goes to 2 is equal to, remember when x goes to 2, this means x is, we estimate the x by 2. So this means x is not equal to 2. When x is not equal to 2, this is your function. Okay, the limit, this is f of 2. So x is equal to 2. F of 2 is 5. But when talk about the limit, x goes to 2 means x is not equal to 2. X is a neighborhood of 2. X is a near 2. Okay, so in this case, you have to find the limit of this function. X squared minus 4, x minus 2, when x goes to 2. Okay, so from now on is a popular limit. If you substitute, what's going to be the result? That gives you 2 squared minus 4. And that would be 2 minus 2. 2 squared would be 4. 4 minus 4, and this is going to be 0. That gives you 0, 0. What's the message for this one? Message? 0, 0?
Is it not continuous?
No. There is a common factor, yes. Remember when you get the 0, 0, there is a common factor. What is that common factor?
X minus 2.
Excellent, x minus 2. Remember, you have to factor out the top and the bottom to eliminate it. So you see, in case of a continuity, just as soon as we get the definition, the rest is going to be the one that we did before. So we have to go back. We have to go back here. So, oh, I just remind you that x minus 2 is a factor, is a common factor. Okay, it's going to be a common factor. So we have to find it and eliminate it. So this is it. It's going to be limit of, the common factor is x minus 2. And on the top would be x minus 2 times x plus 2. You see, when x goes to 2. Now we have the common factor. There you are. This is the common factor. Eliminated it. That gives you 1. So the leftover is going to be, the leftover is the limit of x plus 2 when x goes to 2. Now if you substitute that, give you 2 plus 2, which is equal to 4. So the limit of the function, the limit of f of x when x goes to 2 is equal to what? Is equal to the 4. And f of 2 is equal to 5. You see the limit is 4, the value is 5. They are different. So this means the limit of the function, okay? So this means that the limit of the function and the value of the function are not the same. When they are not the same, at this point, we are going to get a gap. You get a hole, if you like. So this means this function is not going to be continuous. Okay, so the conclusion is going to be the limit of f of x when x goes to 2 is not equal to the f of 2. So this means f is not continuous at x equal to 2. F is discontinuous or not continuous. F is not continuous. Not continuous at x equal to 2. If you graph it, there is going to be a hole, between these two formats that you're going to have. Okay, so this is the notion of the continuity. In the history of calculus, they didn't bother about the continuity at the beginning. We did have calculus without continuity. And the reason was when they used calculus at the first time, they just applied to the polynomials. And the polynomials are continuous forever. So that's why they didn't bother. But if you want to, this is calculus for, just for one variable. If you are going to be measuring physics, not in your case, you are going to have to be doing the 2-dimensional or 3-dimensional. When you go to the higher dimensions, this notion of the limit is not going to be working very well. So what we do, we replace that notion of the limit by continuity. So that's why the continuity will replace the calculus, if you like, in advanced level. And it's going to be interesting at this level too. Okay, so what we're going to do, so we go back, whatever you did for the limits, you can do it for the continuity. Remember, we have computing theorem. Remember the computing theorem? The sum, the limit of the sum of the limits, the difference, the product, the quotient. So what you can do is you can go back to that theorem. Anytime you did have a limit, replace it by continuity. So what does it mean? This means if two functions are continuous, then the sum of the function, the product of the function, the quotient of the function, all of them are going to be continuous. And that will help us to be able, because the question would be given and you want to check the continuity for us, okay? So we give you one nice theorem that thing makes things so easy for us and we can answer all the problems, okay? So let's have a theorem. This theorem would replace the computing theorem. So you can use this one anytime you like in order to check the continuity of the functions. We give you two questions on this one. As soon as I write it down, then you realize that we already done it. And in fact, the question number 1 on the quiz is of this nature, if you like. But we just ask you find the domain of the function, but we're going to give you again, but in your test, and we ask you, where the function is continuous. You will find out it's going to be the same question, okay? So let's have the theorem over here, and that's it. This theorem would have a couple of parts as we did it for the other one. So let's start with the first part. First part, the combination of continuous functions is going to be continuous. So there you are. If you have two functions, if the functions, okay, if the functions f and g are going to be continuous, okay, let's say on the domain D, then there you are. Then the functions, now what's going to be the functions? There you are. F plus g, the sum of the two functions. F minus g, the difference of the two functions. Okay, f times g, the product of the function and their quotient. And f over g. Of course, we know that this is going to be with g not equal to the 0. Okay, are also continuous. Continuous functions. You see? Because if you want to prove it, you know that the limit of f plus g is the limit of f plus limit of g, as we did it before. But for the continuity, the limits and the value of the function are going to be the same thing. So you get exactly the definition of a continuity, that the limit of the function and the value of the function happen to be equal to each other, okay? So that will help us in a minute, you will see it, us to be able to get the continuity of famous function. In particular, this one, number 2. Remember polynomials. And we did it. If you want to find the limit of the polynomial, just substitute. So all the polynomials are continuous. Okay, so there you are. If p of x is a polynomial, that's why we like polynomial, is a polynomial function. Okay, so if it's going to be a polynomial function, then p of x is continuous. P of x is continuous. Continuous everywhere. Everywhere on, okay, on the domain which is a negative infinity and positive infinity, or just d equal to the r. The best case. So if you give a polynomial, no question about it. You don't need to do any extra action. As soon as you see the polynomial, you can claim that this polynomial is continuous everywhere. Any question? Give us an example of a polynomial. One example. Example of polynomial.
F of x equals 4x squared plus 2x.
That's it. Yes, you have to know this polynomial. See, repeat it for yourself so that you know them because they are going to be used. That's why you see anything we talk about it in this course is easily applied to the polynomials. That's why we like them. So we want to make sure that you repeat it for yourself. Always have examples of a polynomials. So the polynomials are going to be continuous. You see, in mathematics, I don't want to make it difficult for you, but it's nice to know at least the history of calculus. You see, as you can see, polynomials are very nice, are continuous. So after polynomials, if you want to find a nice function, that function is a continuous function. So polynomials are continuous everywhere, nice, okay? And if you want to find the next nice function, is going to be continuous function. This notion of the continuity was given by a German mathematician. His name is Weierstrass. Great mathematicians, okay? That is going to be Weierstrass. That's it. He's responsible for the nice calculus that you have it. You can search on internet to see what he has done for us, okay? The notion of the continuity is due to the Weierstrass, and he just polished the notion of the limits. But then he proved another theorem. The theorem is that, look at these two that give a better understanding. Remember, we have polynomials and the continuous function. He proved that every continuous function can be approximated by a polynomial function. This means continuous function and the polynomial function basically are the same thing. And this is what you can do today with your calculator. You can estimate it, okay? The continuous function can be estimated. It's a kind of, any continuous function is going to be a limit of a polynomial. This theorem is very important in mathematics. We call it Weierstrass approximation theorem. And when we go on, in very serious science fields, when you want to prove something in advanced level, they say, oh, try polynomials first. They try the polynomials. If that phenomena is satisfied for the polynomial, they say, oh, okay, now by the Weierstrass theorem, we can apply to any continuous function. So it's such a great theorem that we call it, Weierstrass approximation theorem. We cannot prove it, at this level. You have to get to the, at least first year of a master program to be able to prove it. That theorem by the Weierstrass in the modern time has been extended by a great American mathematician. His name is Stone. Okay, I met him a couple of years ago. He was alive. Stone. So we just put them together in mathematics and we call it a Stone-Weierstrass approximation theorem. Search on internet, you will see it. Such a great job that show you that how important continuous function are going to be or a polynomial function. Okay, that's just a piece of history if you like that. Okay, so you remember. That's why I emphasize all the time. I say, oh, give me a polynomial, because there is nothing else. All of them are polynomials. Okay, so the polynomials are continuous everywhere, and they are very close to a continuous function. That is 1, 2, where I give you a 3 only, and then we finish it. What's the third one? Remember, when we want to find the limit, we say that sometimes we may get a piecewise dependent function. Okay, so just remind you or recall that. Remember this one, the limit of f of x when x goes to a. We say that it's equal to L, but for the continuity, it's going to be f of a. if and only if. You see, when the limit exists, the right limit, remember, the right limit and the left limits must be the same. So if and only if the limit of f of x, when x goes to a negative from the left, is equal to the limit of f of x when x goes to a positive, and that's also equal to the f of a. So we say that the limit of the function does exist if the right and the left limit does exist. But now we can use another expression. When this limit happens, this means f is continuous. So this means f is continuous at x equal to the a if and only if f is continuous at a from the left and from the right. So when it's a piecewise defined function, you have to do the right limit and the left limits. And anytime they are going to be equal to the f of a is going to be right and the left continuity. You are going to have just a couple of examples of this type. But in case you see it, so you are ready for it. So this is going to be the recall. So equivalently, now we can say that equivalently, this means f is continuous. F is continuous at x equal to the a if and only if. If and only if f is going to be continuous. F is going to be continuous at x equal to the a from the right or from the left, and the right, if you like, and the right. So we call it one-sided continuity, and we're going to use it when we get to the a piecewise defined function. Okay, so this theorem is going to be the key for us to be, especially that part 2, that the polynomials are going to be continuous. Okay, so your job is we give you a list of the function and we ask you to show that where these functions are going to be continuous. Okay, there are a kind of the kind of 7 types of functions, and we put them into 2 questions, and we're going to question you at the next test. And you already have seen a version of these ideas. Okay, so this is going to be the only examples that we need to know. Any question? So what is that example? Your problems are here. Okay, so example, we wanted to check determine where each function, where each function is continuous, Okay, that's going to be one. So there you are, one by one, and we can use that theorem that we talked about it. Are you ready? Number 1, the most popular one, f of x equal to, you see this function quite a lot from now on, x cubed minus 5x squared, plus 2x minus 10. We want to know where this function is going to be continuous. What type of function is this one?
Polynomial.
Polynomials, that's it. Polynomials, and according to our theorem, you see, polynomials are continuous forever. That's it. So solution, you have to mention this word polynomial. F is a it's like finding the domain of the function. It's the same thing. F is a polynomial. F is a polynomial, and so is continuous everywhere. Is continuous everywhere. Everywhere on the domain R. You can say negative infinity and positive infinity, or R. We accept both. That's it. So on the test, you have to mention that it's a polynomial. When it's a polynomial, it's continuous everywhere. That's it. That's it. First class. Easy. Any question? So that's a type 1. What's a type 2? Type 2, we did it before, a quotient function. Start with this one, g of x equal to 3x plus 1 over 3x squared plus 1 over x minus, minus 3. You see, that's a quotient function. The top is a polynomial. It's continuous. The bottom one is a polynomial. It's continuous, but you divide. When you divide, remember, when you divide, you have to exclude. You must make sure that the denominator is not going to be, is not going to be 0. So exactly as you did before. Solution. Remember that idea of the free agent, negative infinity, positive infinity. We have to exclude where the denominator is 0 at 3. So you have to exclude the 3. That's it. So this function is going to be continuous everywhere except at x equal to 3. Or it's going to be continuous in this portion. Okay? So you let the denominator equal to the 0 as you did it for the domain. Exactly the same thing. So that gives you x equal to 3. That's a gap. X equal to 3 is the whole, the gap. So you are going to claim that the g is continuous. G is continuous. Okay, if you like the explanation, it's continuous everywhere. Everywhere. Except when there is a hole. When x is equal to 3. That's one way to write it down, and we accept it. Let me prepare interval notation. Or this is better, you see, or that's it. G is continuous. G is continuous on the domain. What is the domain? Two portions. Negative infinity up to the 3. Parentheses, remember, because there is a hole. Union with 3 and positive infinity. We prefer the second one. And even if you write the first one, we accept it. Okay, so it's a quotient function. It's continuous on its domain. What is the domain of the quotient function? You check to see if the denominator is 0. The denominator is 0 at 3, so we have to remove the 3. So this is the domain of the function. At the same time, since you're dealing with the polynomials on the top and the bottom, so this function is going to be continuous on its domain, and you're done. Any question? Now you find out why I start with this type of function as a review for you, because I want you to prepare you. Okay, and then you just that you be rewarded because you don't have anything else to do for us to get the continuity. Okay, that's the type 2 question. We just repeat the type 3. Remember, the type 3 is going to be, we may exclude more points than the denominator. H of x, x squared plus 5x plus 1. Denominator x squared minus what? Minus 16. Same thing. The top polynomial continuous, the bottom one polynomial continuous, but since it's a fraction, you have to take care of the denominator. Remember, this is x squared. You have to factor it first to find out how many numbers are you going to exclude. That's it. So for the solution, so you rewrite it. This is h of x equal to, so you have x squared plus 5x plus 1 on the top. Then you factor into the x minus 4 times x plus 4. So you have to remove 2 numbers. Okay, you have to remove the 4 and the negative 4. That's it. Remove the 4, so there is a hole here, negative 4, and remove the 4, another hole here. So this function is not continuous at x equal to negative 4 and not at x equal to 4. Everywhere else is nicely continuous because of those holes. Okay, so there you are. H is continuous. Continuous on the domain. Domain, remember 3 portions. 1, 2, 3. The first one, negative infinity to negative 4. The second part, -4 to 4. The last part, 4 and positive infinity. So this is it. You get -infinity to -4. Remember, a parenthesis, no bracket, because you remove it. Union with -4 and 4. Union with 4 and positive infinity. This is where this function is going to be continuous. Again, it's a domain. It's a domain of the function, but since we're dealing with the polynomials, this function is going to be continuous. So it's going to be continuous everywhere, except you are going to have two holes, one at the -4 and one at 4. Any question? So it's the same idea as before. Remember, there was one special case for this one, so that is going to be the special one. What was the special one? This was the one that you cannot factor out the denominator. See, this is going to be x squared plus 5x plus 1. But the denominator would be x squared plus 9. Remember x squared, you see, again, we get polynomials, the top, the bottom, so everything is nice, continuous. But we have to check to see if we can factor this one. Remember x squared plus 9, you cannot factor it. You can only factor x squared minus 9. Since you cannot factor it, there is not going to be any hole. You see, so the function is going to be continuous everywhere. So this is it. You have to explain it for this one that, okay, you're explaining the fact that x squared plus 9, as we talked about it before, is not factorable. Is not factorable. When it's not going to be factorable, okay, this means you cannot make it 0. And so it's never 0. Okay, it's never 0. So that's it. So the function f is going to be continuous everywhere. F is continuous. Is continuous everywhere on the domain of -infinity and positive infinity. Okay, so you get the number line, no hole in it. So the function is going to be continuous for all the values on the number line. Any question? Again, these are all the domain of this function. You see, the functions are nice because they are ratio of the, okay, they are ratio of the polynomials. So that's why the polynomials are continuous. So you have to be only careful about the, okay, about the nature of the function. If it's going to be a radical function or it's going to be a rational function, you have to be careful. Otherwise, it's nicely done. Okay, any question? So that's a rational function. Remember, we did have another group of the functions. The other group was what? Was the radical function. So same thing for the radical function. So that's a 4. So we get to the 5th one. For the radical function, again, the same story. You have to take care of the index of the radical. So suppose you have this one, f of x equal to the square root. Okay, square root of x plus 4. You see, if you remove the radical, x plus 4 is a polynomial. It's continuous. But the question is going to be, can you take it out of the radical? Remember, we look at the index of the radical. If the index is even, you have to do extra things. But if the index is odd, it's going to be continuous everywhere. So as we did it before, we check the index. Index, remember, for the square root is 2, is even. When it's even, you have to guarantee that it's never negative. So you can say now that f is continuous. F is going to be continuous, means it's going to be defined when x plus 4 is greater than or equal to 0. Greater than or equal to 0, solve it. It's going to be x greater than or equal to -4. So this is going to be the restriction that you're going to have. So this is going to be your number line, -infinity to positive infinity. and you have a -4. It's a solid point because we have the equality here. So it's going to be -4 up, -4 up. So the function is going to be continuous between -4 and a positive infinity. So f is continuous. F is going to be continuous on this domain. So what the domain? Domain is going to be -4 and positive infinity. That's going to be parentheses, but this is going to be a bracket. That give you the continuity of the function. Any question? Again, it's nothing new because the domain of the function, we already talked about it. But the thing it's new is the notion of the continuity. But since you're working with the polynomials, are continuous on the domain of the function. Okay, that's the even index. We need odd index. Again, as we have it, you did have one odd index on the quiz. Question number 1, I think that's the third case, or the third part. So that's it, something like a cube root. And this is going to be x squared plus 5x plus 7. You see? Inside the radical is a polynomial, it's always continuous. But can you take these numbers out of the radical? Yes, because the index is odd. Remember, cube root. We can have cube root of a positive number. Cube root of 8 is 2. Cube root of -8 is -2. Cube root of 0 is 0. So always we can work. So this function is going to be continuous forever. Okay, so solution. Then index of this radical. Index 3 is odd. That's it. You know that domain of function is all real numbers. So this is going to be continuous everywhere. So G is continuous. G is going to be continuous everywhere. Everywhere, if you like, on the domain, which is R, or -infinity and positive infinity, and you're done. Any question? So we did have all the 6 cases before, but we just focus on the domain of this function. Now, these functions are nice. Okay, it's going to be nice, and they are going to be continuous one piece on their domain. So we call them the domain of the continuity. Okay, any question? Now, these were all nice from the past. There is one more case, very important case, and that is a piecewise defined function, which is different. Let's say I'm going to check a piecewise defined function to finish it. Okay. So this is going to be 7 times that I promise you. So that's it. Example. Your book like it very much, and you have quite a lot of this on your assignment. So we give a function as usual. Suppose we have a piecewise defined function. F of x is going to be equal to, there you are, piecewise defined. F of x equal to the x cubed minus 5x plus 1 when x is less than, let's say, -1. Okay, less than -1. And you have something like 5x plus 3 when x is greater than or equal to the -1. You see, if you forget about this, these are polynomials and they are continuous. But when you partition it, the only thing that you have to check is this partition point. Remember when we graph it, like the one that you got on your quiz. When we graph it, we get 2 pieces. When we graph, we get 2 pieces. And we talk about that you have to consider the partition point. So what you're going to have, you made these 2 pieces will be connected together. If it's going to be connected together, this function is continuous forever. But if at this partition point there's going to be a break, in that case, this function is going to be continuous everywhere except at x equal to -1. So that's why you have to check the continuity at the -1 only. To check something at the partition point, we talked about it before, you have to check the limit. So you check the right and the left limit at x equal to -1. If the right and the left limit happen to be equal to each other, since you have the equality here, this function is continuous forever. But if the right and the left limits are different, this means there is going to be a break in the graph of this function at x equal to -1. So in that case, that function is going to be continuous everywhere except at -1. Okay, so we have nothing to worry about at any other. So this is the way I'm going to describe it for you. You see, to start with, if you forget about this point, you can say that f is continuous. F is going to be continuous if x is not equal to -1. So what we're going to do, this is for your information. You can do it right away. You check the continuity. You check the continuity of f at x equal to the -1 by finding or checking, by finding, okay, one-sided limit, means right and the left, one-sided limit of f at x equal to -1. See, that's what we are going to do for us. Okay, if you forget about that -1, these are polynomials or continuous. But the difficulty is -1 because if you go a little bit to the right or to the left, we get two different functions. So the question is going to be, are those functions are going to be meet each other at x equal to -1, or are they going to be disjoint? So that's why you have to, you have to check it. Okay, so we check. This is it. We check the limit of f of x when x goes to -1 from the left. Now you know it. When x goes to -1, negative means x is less than -1. When x is less than -1, you have to use the first part. So it's going to be equal to the limit of x cubed minus 5x plus 1. When x goes to -1, negative. From now on, you just substitute. -1. Use parentheses, -1 cubed minus 5 times a -1 plus 1. Carefully simplify it. -1 cubed would be negative, -1. Negative, positive, a positive 5. Okay, and the plus 1. You simplify that, give you 5. Okay, so the left limit is going to be 5. Question? Check the right limit. So what's going to be the limit of f of x when x goes to -1 positive this time? -1 positive, we know that x is going to be greater than -1. So the function to be used is this one, 5x plus 3. So it's going to be equal to the limit of, okay, 5x minus 3 when x goes to, okay, plus 3. Plus 3 when x goes to -1 positive. Okay, just substitute -1 again. Remember, this positive is just a direction. So that will give us a 5 times a -1 plus 3. So that gives a -5 plus 3, which is a -2. You see? They are different. Since they are different means they are not going to meet at this point. So there's going to be a hole at that point. Okay, so you just claim that you can write down in this format. 5 is not. If these two numbers happen to be the same, your function is continuous everywhere. Your function will be continuous at the partition point, and therefore it's going to be continuous everywhere. But if these two numbers are going to be different, so this is going to be there is a hole. Okay, so this means f is not continuous. F is not continuous at the partition point. Not continuous at x equal to the -1. Okay, so what's going to be the conclusion? The conclusion is, so this is it. You see, this is a number line, -∞ to +∞. and that was a -1, we cannot check the continuity here. Okay, because they are not going to be the same. So this is going to be the domain of the continuity. So f is continuous. F is going to be continuous on everything except -1. So this is it. Domain would be, you start from the -infinity, you arrive at the -1, but it's open. Union with -1 and positive infinity. Okay, or in word form, if you like, f is continuous everywhere. You see, equivalency, if you don't like this one, you can say that f is continuous. F is going to be continuous everywhere. Everywhere except when or where x is equal to the -1. You didn't get it at the partition point. So there are examples that this right and the left limit happen to be the same thing. So in that case, your function is going to be continuous forever. But if you get two different numbers, the function is going to be continuous everywhere except at the partition point. So this is a collection of the continuous function or the problems that you're going to have. Okay, you are not going to have any more. You know, if you are going to be taking calculus 1, 2, 3, of course, you have trigonometric function, sine, cosine, tangent, but not for this course. As you can see, the idea was new, but the operation that you did is exactly the one that you did before, except this last one. You did before in order to get the to get the domain of the function. If you just let me just give you quickly one more, so that you see what would happen if they are going to be equal to each other, and then we're done. Okay, question. So that's a red flag that you have to be careful. Let me just quickly give another one. See what would happen if they are equal to each other, and then we're done with this chapter and this section. There you are. Check this function. Suppose something easy so that we can do it quickly. It's going to be x squared if x is going to be less than 2. And it's going to be 2x when x is greater than or equal to 2. Okay, we want to know where this function is going to be continuous. Okay, so determine, if you like, determine, as we did it before, where f is continuous. You see, it's partition at 2. As we talk about, you just check the continuity at x equal to 2. You check the right and the left limits, because everywhere else is continuous already. Okay, so what you do, you just check the right and the left limit of f of x, when x goes to 2 negative. 2 negative means x is less than 2, the function is x squared. So it's going to be limit of x squared. When x goes to 2 negative, you substitute the 2 squared equal to 4. Okay, that's a left limit. So how about the right limit? We check the limit of f of x when x goes to 2 positive. 2 positive means the function x is bigger than 2, so the function is 2x. So it's going to be limit of 2x when x goes to 2 positive. If you substitute 2 times 2 equal to 4, you see. That's exactly what I talked about. See, that's why. So the first portion and the second portion connect to each other. So it's continuous forever. Okay, so 4 is equal to 4. So this means this function is continuous forever. Okay, f is continuous. It's continuous everywhere. Everywhere on the domain, which is R. See? That's a difference between this is the second case, alternative case for the these piecewise defined function if you want to check the continuity. Okay, so You're just going to be bothering about that partition point connection. So if you compare it, you see the previous one, the partition point was a -1. So we check the right and the left limit, two different numbers. So we cannot connect them together at -1. So that's why this function is going to be continuous everywhere except at -1. And this is going to be the continuity domain. But look at this one. So again, you check the partition point. You find the right and the left limit, same number. So this means it's going to be connected to each other. And this function is going to be continuous forever. That's it. That's 1.6. Any question? Two questions of these sections. We give you all these functions you solve here. We put them together in the combination of two problems. And we ask you to check where the function is going to be continuous. That's a chapter 1. So we are ready to take the first problem of a calculus. I talk about it. This is just the estimation. So the first problem of a calculus is going to be called tangent line problems. We are going to be very busy with this chapter 2 quite a lot. That will take us almost to the